Morning, everybody. Hope you're all doing well. We're going to finish up chapter 10 and get a little bit three-dimensional here. So everything thus far that we've been working on, we've been doing on a flat sheet of paper, right? We're still going to have to kind of do it in 2D, but we're going to want to expand it out into a three-dimensional space. So, we've got Lewis dot structures, like for instance, this thing here, this resonance structure. But this isn't actually what it looks like. It's not flat on the paper like that. Same thing with like these here. It's not that there's a phosphorus in the center and all these things exist on a plane, like a pizza, right? Like slices of a pizza. That's not the case. And so we need to go over this thing called VSEPR, VSEPR, which is valence shell electron pair repulsion theory. Blah, 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 right? It is just a fancy way of saying that groups of electrons want to get as far away from each other as they possibly can. Okay, so if I have two single bonds, the single bonds are going to spread out in 360 degrees to get as far away from each other as they can. It's important to talk about what is considered an electron group. A lone pair is considered one electron group, okay? A single bond is considered one electron group. Multiple bonds are also considered one electron group. So sometimes people will see a double bond and they'll think, oh, that's two electron groups, but that's not actually the case. Why? Because let's say I have CO2, which is, we've got carbon in the center and we've got oxygens on the sides, and these are double bonded, and then there are two here. These double bonds can't get away from each other, right? They're behaving as a unit. So I'm not going to take into account that these are two separate things because they can't break apart. So this would be considered one group. This would be considered a second group. So I would say this thing has two electron groups. Electron groups also are only important on the central atom when we're talking about the shape, okay? So do you see how there are these lone pairs on the outer ones? This here, these oxygens have these lone pairs. Those don't affect the shape. The only thing that affects the shape is what's happening at this central point. Because everything, you've got that central point and everything radiates out from there. So these things don't play into that shape or the radiation. So these separate groups want to repel each other, and that gives a predictable shape. So let's look at the most simple one here, and it's actually what we were just talking about, carbon dioxide. So in carbon dioxide, on the central atom, I would say that I have two electron groups. Here is the first electron group, and here's the second electron group. Remember, we don't care about, we care about the electrons on the outer things when we're drawing the Lewis structure, but when we're trying to predict the shape, we don't take those into account. So 1, 2. All right, if I have two electron groups, you can kind of think of it like there's a ring in the center, and then there's these ropes hanging off of it. And the ropes coming off of it need to stretch out in such a way to create some sort of balanced structure, right, where the ring doesn't move. So, or how far away can the electrons get and repel each other? And that would be 180 degrees. So we would call this thing linear, very simple. This thing has a linear structure. Now notice that there are no lone pairs of electrons on the central atom. That makes the geometry much easier to predict, okay? Because we've got one group, two groups, no lone pairs. Nice, easy peasy, simple. Let's look at a different shape. So let's look at this one here, H2CO. This one is a little bit more complicated, but it follows a similar principle of count up how many groups are around the central atom. So here I've got 1, 2, and 3. Remember, a double bond counts as one electron group. So there's a total of 3 electron groups. So in your head, visualize a ring or some sort of central ball, and you have 3 ropes coming off of it. How can you get those 3 ropes to stretch out in such a way that you will create a balanced structure? Or if you think of them as negative ends or negative tails, how can they get as far away from each other as they possibly can? Well, that's going to happen at 120 degrees, which is known as trigonal planar geometry. Why is it planar? Because it is in fact flat. Okay, so it's flat like a pizza. So linear is also somewhat flat. I mean, it's kind of flat from all directions because it's only a line. But this makes up a 2-dimensional shape that's flat, and there's roughly 120 degrees. Now, some of you may be thinking, okay, but this is a double bond, so there's more negative electrical charge there. Shouldn't that push these away or repel those more? That does happen. Double bonds do have a higher effect, but for the sake of this class, just go with it's roughly 120 degrees. All right, so we're not going to say that there's any sort of difference between a single or a double bond. So this one is thinking about, you have a pizza and you cut that pizza into thirds. So we've got our linear, we've got our trigonal planar. Now, the next thing I want to do, before I even go to the slide, is I'm going to have us do the Lewis dot structure for methane. So methane is CH4, just to reignite Lewis structures. I want you to draw me the Lewis dot structure for CH4. Shouldn't take too long. It's a simple one. Okay, so this thing has 8 valence electrons. I'm going to put carbon in the center and take the 4 things and put those on the sides. Also, hydrogen is a terminal atom because it only likes a duet. I have 8 electrons. I got to stick it together. So I'm going to stick it together. That's all 8 electrons. Just double check, make sure everybody's happy. Everyone is happy. Hydrogens only want 2, carbon wants 8. Okay. So how many electron groups do I have in this structure? We'll go to the central atom and see how many areas of negativity there are. 1, 2, 3, 4. 4 electron groups. So a lot of times we will look at this and think, oh, okay, so this is something like square planar. Or there's like 4 groups and it's on a flat piece of paper. That is not what's happening here, okay? These things are coming forward and back in space because if it was like this, what would be the angle here? What's the angle at a right angle? 90 degrees, right? So the farthest they would be getting away from each other is 90 degrees. But that is not actually what's happening. Instead, and I cannot draw if my life depended on it, so I will use the slide for what it looks like. It looks like this. It's called a tetrahedral. And you can sort of see it as like a little pyramid with a little booper sticking up on top. So 3 of them sort of point down and one points up. These have an angle of 109.5 degrees between them. So that is effectively farther than the 90 degrees. So know that just because it kind of looks like it's square planar when you're drawing it, what's actually happening in space when you have 4 electron groups is this thing right here called tetrahedra. You may have heard of tetrahedrals before, tetra being 4. So now we've got linear, we've got trigonal planar, and we've got tetrahedral. What you'll notice with those first 3 that we've seen is they all have had only bonded pairs, right? There haven't been any lone pairs of electrons on any of those examples. So what we need to do is talk about, well, what happens if instead of there being an atom here, there's a lone pair of electrons? So we have to separate out our geometries into what we call the electron geometry and then also what we call the molecular geometry. So thus far, what I've been teaching you is the electron geometry. That's just where the electrons sit, right? If there's 4 electron groups, it's tetrahedral. If there's 3 electron groups, it's trigonal planar. If there's 2, it's linear. But now we want to tack on another thing called molecular geometry. Molecular geometry is where the atoms actually sit. So if you have an atom attached to every electron group, these 2 things will be the same, right? Because the electron groups have a molecular structure that parallels it. This differs, these 2 will differ anytime you have a lone pair of electron on the central atom. Because now what you've got is a electron group that doesn't have a buddy. And that lack of buddy or that lack of atom means that these 2 ideas split. So let's look at this thing here. This is ammonia, NH3, 8 electrons. So this is the structure. This is what it would look like. 3 of the electron groups are bonded to atoms. 1 of the electron groups is lone. It's a lone pair. So counting up the total number of electron groups, whenever we're calculating electron geometry, just count the electron groups. So I've got 1 here, 2, 3, and then the lone pair does count as an electron group for 4. So we would say the electron geometry is tetrahedral. That's nothing new. The molecular geometry, though, is going to be different because of this lone pair of electrons. So let's see what the image looks like. It looks something like this, right? So it kind of looks like that pyramid that we had with tetrahedral. But what's going on with the lone pair is there's no atom sitting there. There's nothing there. So the molecular geometry, or how the atoms are arranged, it looks like this. There's the central atom and there's 3 things pointing down. You seeing how that's different than our tetrahedral over here, where we had 3 things pointing down and 1 thing pointing up? Here, we only have 3 things pointing slightly down. So this geometry, where you have 4 electron groups and 1 of them is a lone pair, is known as trigonal pyramidal. And that sounds very similar to trigonal planar, but it is not the same thing. Trigonal pyramidal means that the 3 are pointing down to create a pyramid shape. Trigonal planar, which we had a couple slides back here, there isn't any lone pair. These 3 are in the same plane. This is our pizza, right? This is our half-Z pyramid. Any questions on that? On how the lone pairs can affect the shape? Because this, just because there isn't an atom there, it's still pushing down on these. So instead of it being trigonal planar, it makes a pyramid shape because these want to get away from it. So you kind of got to think of your original shape, electron geometry shape of tetrahedral, and rip an atom off the top of it. All right, so I've got my tetrahedral, and if I rip the top atom, it makes this little shape here. And normally, again, when I teach this, we're in like a lab setting, and I have these 3-dimensional shapes for you to look at. So hopefully these drawings can help some. Let's do water. Yeah. So water, H2O, It has a total of 8 valence electrons. The structure looks something like this. So I've got oxygen in the center, I have hydrogens on the side, and then there are 2 lone pairs. So as far as the electron geometry is concerned, we still add all the electron groups up. So this has 1, 2, 3, and 4. Each pair, each lone pair counts as 1 electron group, okay? So yes, double bonds, we count as 1 electron groups, but 2 lone pairs, we don't count those as 1 electron group. We would actually count those separately. So 4 electron groups means that the electron geometry of water is tetrahedral. It's the same electron geometry is this. What's the difference here though? This has 3 atoms to a pair off. How many does this have? This only has 2 atoms. And so a lot of times people will look at this structure and they'll just jump right off and say, oh, well, that's linear. Well, it's actually not linear. I mean, it kind of looks linear on how it's drawn on the paper, but let's look at the structure here. So the electron geometry tells us that there are going to be 4 points. Okay, we rip off the atoms from these 2 points. What remains is a corner of your tetrahedral. That's at an angle, right? So this becomes what's known as a bent structure, or sometimes it's called a V shape. So know that either one of those is acceptable. So yes, on 2D, it can kind of look like it's flat. So you have to extrapolate it into 3 dimensions. If it's a tetrahedral, for its electron geometry, again, visualize your little tetrahedral pyramid and then pop 2 of the atoms off. And what you're left with is a corner bend. Yay, nay, maybe. I find sometimes that my artists, Carrie, who knows? I find sometimes my artists do well with this because they can they have this like 3-dimensional quality to them. It does work well with marshmallows and toothpicks. So it's an excuse to eat a bunch of marshmallows if you want to. Let's look at this here. So this is everything that we talked about in a chart. Traditionally, I would have you memorize all of this. For this class, because of the nature of the semester, you can reference this, but you want to be able to read it. Okay, so what we have for these first, well, I'm going to star. So this one, and this one. In these, the electron groups and the bonding groups are the same. Or you have 0 lone pairs of electrons, right? So no lone pairs. So anytime the number of electron groups and the number of bonding groups are the same, or the electron groups, every electron group is attached to an atom, that means the electron geometry and the molecular geometry will also be the same. Okay, so you can just assume if there's no lone pairs, these are the same. It gets trickier in these here. These are the ones that tend to give people some trouble. Right here, where you have a difference in your electron group and the bonding pairs or the lone pairs. So you have some sort of lone pair. There, your electron geometry will change from your molecular geometry. So we can see here, if I've got this here, 3 electron groups. So think about, in your head, think about 3 electron groups. That means the trigonal planar, right? That's your flat pizza cut into 3 groups. What if only 2 of them are bonded? Okay, well, think about your pizza and rip off, one of those atoms. What you're left with is this shape here, which is bent. If we go to this one here, you have 4 electron groups. That's your tetrahedral. So think of your 3-dimensional tetrahedral pyramid, but only 3 of them are bonded. Rip off the top atom. What are you left with? That trigonal pyramidal shape. Do you all see in how to read this? You got to let me know if you don't understand what these things are. Electron groups is all the groups on the central atom. Bonding groups are just the ones that are attached to atoms. And then lone pairs are any of the lone pairs. So let's try some. Let's see if you've got it. I'll give you some examples. And I want you to draw the Lewis dot structure. I want you to tell me what its electron geometry is, and I want you to tell me what its molecular geometry is. And if they happen to be the same, that's fine. I still want you to tell me each. So let's do SO4 2 minus, SO3 2 minus, and SO3. So you'll do the Lewis. You can't do the geometries if you haven't done the Lewis dot structure or it's provided. So you have to do a Lewis structure first. Then I want you to tell me the electron geometry. And do know that sometimes electron geometry, they replace electron with overall geometry. Those mean the same thing. And then I also want you to tell me the molecular. This is all electron groups. This is talking about what the atoms are doing. So that's going to take you guys a little bit of time. So I'm going to give you, it's 9:52. I'll give you 7 minutes to work through that. If you want to do all the Lewis structures first, do that. If you want to do it one at a time, that's fine. Please, though, make sure you are taking into account charges. Okay, those do have an effect on the shape. So that was quite a bit of stuff to do there, 3 of them. I'm going to just do the Lewis structures for each of them. So this first one, sulfur has 6, oxygen also has 6 times 4, and then 2 minus means, so it's 6. Let me just write it out. Oh, come on. Stop popping up on me. So 6 plus 6 times 4 plus 2, because remember, minus 2 means we're adding 2 electrons. So you should have a total of 32 electrons for this one. This one over here is 6 plus 6 times 3, also plus 2. This is a total of 26 electrons. This last one is 6 plus 6 times 3 for a total of 24 electrons. Any questions on that, on how I calculated those? If you don't calculate those correctly, it will have a cascading effect. You'll see right here, these two are so similar to each other, but that charge makes a difference in its geometry, okay? So let's do the Lewis structure. So if I have 32 electrons, I'm gonna put sulfur in the center. I'm gonna put the 4 oxygens on the side. Gotta stick them together. And then I'm gonna make the outside guys happy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 32. Okay, all electrons on the board. When you do a polyatomic ion, you can put it in brackets and put the charge around the outside. So we're done with that. So as far as its electron geometry is concerned, let's look at the central atom. I have 1, 2, 3, 4 electron groups. So its electron geometry is tetrahedral. As far as its molecular geometry, well, one thing you can ask yourself, are there any lone pairs of electrons on the central atom? There aren't any lone pairs, so my molecular and my electron will be the same. So this is also tetrahedral. Think about there being 4 ropes coming off that central atom, and all 4 of the ropes have a partner. If they all have a partner, they'll create a balanced structure. So we're good there. Tetrahedral, tetrahedral. Let's look at this next one here. SO3 2 minus. So I put the sulfur in the center, I put the oxygens on the sides, I stick it together, and then I need to start adding electrons. So these need 6 added. Okay. Right now there are 24 electrons on the board. I need 26 electrons, so I need to put 2 more electrons somewhere. Well, where's the only place I can put them? Is on the sulfur, right? And sulfur needed 2 more anyway, so we are good there. So as far as our electron groups are concerned, for our electron geometry, I have 1, 2, 3, and 4. So what is the electron geometry on this? It's also tetrahedral. The difference here, though, is that here, every rope had a partner. Here, one of our ropes is missing its partner. So think about that pyramid tetrahedral shape and rip off the top atom. What remains is a trigonal pyramidal shape. So it's got a tetrahedral electron geometry and it's trigonal pyramidal for its molecular. You good with that? Who knows? You gotta let me know. And sort of read your face. Carrie, you got it? You're an expert. You're like, no, I'm whipping out the marshmallows later. All right, let's do this last one here. So SO3, it's so close to looking like SO3 2 minus, except it's got 24 electrons. So let's see what happens here. I put the sulfur in the center, oxygens on the sides. I stick it together. I make the outer guys happy first. So I'm going to add 6 electrons to each of these. And right now there are 24 electrons on the board. So I've met that number. Let's check and see if everybody's happy. The oxygens are happy. The sulfur is not happy. Here, we satisfied this sulfur by putting 2 more electrons on it. But here I can't do that, right? So I have to make a double bond. Where could I make that double bond? I could make it off of this oxygen or this oxygen or this oxygen. So that actually makes this thing also known as a resonance structure too. I'm just going to pick this one over here on the right. So I'm going to make a double bond there. I'm going to erase these two. And everybody is, sort of happy. Remember that this bond is sort of intermittently existing on all places. So I'm going to just put some dots here. So as far as its electron geometry, how many electron groups do I have? You consider a double bond one group. So this is 1, 2, 3, 3 electron groups. So think about your flat pizza cut into 3s. Trigonal, planar. Now, for its molecular geometry, ask yourself, are there any lone pairs of electrons on the central atom? There aren't. So then it's real easy. It's going to have the same molecular geometry. This is also trigonal, planar. Same Z. It's when you get the lone pair, that's when it gets kind of sticky, okay? The lone pairs are what make this different.
Can you repeat what you said about the 3 bonds on SO3? About why you determine them also trigonal planar?
So why there are 3?
On the molecular geometry.
Because there aren't any lone pairs of electrons. So what's happening is, do you see how each rope has an atom attached to it? So the atoms are making the same shape the electrons are making. Okay, so this is talking about what are the atoms doing. This is talking about what are the electrons doing. If they all are partnered together, they'll have a parallel or the same structure. What happens is something here. Do you see how this rope doesn't have a partner? That's why they are different. Okay, because the electrons are forming a tetrahedral shape, the atoms are not forming that same tetrahedral shape because one of their partners is missing. Okay, so, and you'll see that again in this chart, anytime there's a lone pair, even if it's 1, if it's 2, it doesn't matter. It's going to have a difference in the shape there. Worst comes to worst, you just read it off of this chart. All right, make sure you know how to identify bonding and lone pairs, and you should be able to get them all. Other questions on that? Okay, we'll move on because you guys do have a test Sunday to Monday. So we want to finish up this chapter. Last little bit here. Yeah. Okay, we can talk about, here we've got something called electronegativity, and then this other term called polarity. And we'll kind of pull in this idea of why oil and water don't mix. So when we put oil and water together, they separate. Why is that the case? Well, it's because water molecules are known as a polar molecule, and I'll tell you what that means in a minute. Oil is known as a nonpolar molecule, and polar and nonpolar things do not like to mix. Polar things, which sort of have a magnetic or sticky quality to them, they want to clump together or stick together, and they repel anything that doesn't also have that sticky quality. So here is water. Water is, sometimes it's called the universal solvent. It is like our classic polar molecule. Why is it polar? Well, I will tell you right now, one of the easiest ways to identify if a molecule is polar, does it have lone pairs of electrons on the central atom? If there are lone pairs, it is polar, okay? So think about the tug of war and you have 4 ropes. 2 of the people decided not to show up for the tug of war. So it creates an asymmetry in the pull, right? Or if we had that ring where all 4 ropes are being pulled, only 2 of the ropes are getting pulled at a weird angle. The other 2 aren't. This whole molecule has an asymmetry or kind of a wonkiness to it. So the asymmetry relates to polarity. So going a little bit farther back, electronegativity is the ability for something to attract an electron. So the higher your electronegativity is, the greedier you are for electrons. So in this case, oxygen is more electronegative than hydrogen. That means that the electrons want to hang out closer to the oxygen than they do the hydrogen. And if you look at where hydrogen is on the periodic chart versus oxygen, hydrogen's kind of over on the left. Those things don't really like electrons, right? They kind of want to give them up anyway. Oxygen is like almost fluorine. Fluorine has the highest electronegativity. They're super greedy for those electrons. So we get, when we have a difference in the sharing of an electron, we get what's known as a dipole moment. And a dipole moment is just where you have the electron sort of hanging out closer to one side. So between the bond with oxygen and hydrogen, this is a probability dot chart. So the probability of where the electron is going to be, we can see the probability is much higher that it's going to be around the oxygen than the hydrogen. And what that does is create sort of like a negative charge by the oxygen and a positive charge by the hydrogen, because the electron just in general sits closer to here. So now we've got this dipole moment, or this asymmetry within the molecule where there's like positive parts and negative parts to it. And that makes it stick to itself. So as far as what you saw here, this is known as a polar covalent bond. Covalent because it's sharing the electrons. Polar because it's sharing it asymmetrically, or there's a dipole moment. Versus something that has the exact same electronegativity. So what if we had chlorine and chlorine? They are equally greedy for the electron, right? They have the same, think of them as like twin brothers. They're the same strength. So they're going to pull the electrons equally. So this is known as a nonpolar covalent bond. They're sharing the electrons and they're sharing them equally. If you have an electronegativity, these are the numbers for all the electronegativities. If you have an electronegativity that has a difference, usually it lies between like 1.5 and like 1.8, you have a polar covalent bond. So hydrogen's over here, oxygen's over here. When I subtract those two from each other, we get a difference that falls into this polar covalent bond where they're sharing them, but they're not sharing them equally. And there's a chart that I like over here. Okay. So if your difference in electronegativity is 0.4 to 0, you have a pure covalent bond, or sometimes it's called a nonpolar covalent bond. This is where they share the electrons and they're sharing them equally. So we can see our electron cloud, our bubble is equally balanced amongst the two atoms. A polar covalent bond is when your difference in electronegativity is somewhere between 0.4, 0.5, and roughly 2. This is where they're still sharing the electrons. There's a difference in electronegativity, but it isn't so great that it transfers the electron. They share them, but they share them inequally. So there becomes a negative side and a positive side. The negative side is the side where the electron is more likely to be. The positive side is where the electron is less likely to be. What if you have a difference that's greater than 2? Well, here the electronegativity is so different. The one thing is so greedy for the electron and the other thing just doesn't want the electron. You just transfer the electron and you become ionic. This is where you have a metal and a non-metal. So if I go back to that electronegativity chart, these numbers don't have any units to them. They set fluorine as like this arbitrary 4. So it has the highest electronegativity. It is the greediest thing for electrons. Everything else is just in relationship to fluorine. So oxygen is 3.5 or 0.5, so whatever 4 divided by 0.5, like an eighth less in its electronegativity. That's where those numbers come from. You can see as you move towards the metal, that electronegativity number drops pretty substantially. So when you have, like let's say we have fluorine and fluorine, 4 minus 4 is going to be 0. That's an equal share of electrons. What happens if we creep over 1, right? Well, there is a difference in the electronegativity of 0.5. It's not the same though, so they're not going to share them equally. The electron is going to kind of hang out by the fluorine more. What if we go with something over here? The electronegativity there is so different. This thing is so greedy, it's just going to take the electron from cesium. So that's where those numbers are coming from. This chart, I would give you the specific numbers. Okay, I wouldn't expect you to memorize this. I could say something like, hey, fluorine has an electronegativity of 4, and nitrogen has an electronegativity of 3, and carbon has an electronegativity of 2, which has a, more polar covalent bond. The one that has the bigger difference has the more polar of a covalent bond until it becomes so great that it just becomes ionic. So you do want to be able to differentiate these. Both of these things over here are molecular, right? Or both of these things are sharing electrons. This is just sharing them equally. This is sharing them unequally, and this is transferring. So back to how this has an effect on a molecule being polar. Well, if you have a bond that's polar, like 2 adjacent atoms aren't sharing the electrons equally, that doesn't necessarily mean that the bond is polar. Does the presence of one or more polar bond in a molecule always result in a polar molecule? Not necessarily. A polar molecule is one where the polar bonds, when you add them together, they don't balance or cancel each other out. Okay, so you get a net asymmetry. Again, an easy way to think of this is the lone polar bear. The lone polar bear. If there are lone pairs, it's polar. Let's look at an image of that over here. So if we look at carbon dioxide, carbon and oxygen have difference in electronegativities. They don't share the electrons equally. The electrons are going to want to sit closer to the oxygen. Oxygen is greedier. But look at what's happening. This oxygen is pulling on these electrons, and this oxygen is pulling on these electrons. So it's like an even pull. Sometimes they draw the electron, like which direction the electron is going, as a vector or a line. If those vectors are equal and opposite to each other, the whole molecule is non-polar. So this would be considered a non-polar molecule. The bond between the adjacent atoms is polar, but the whole molecule is nonpolar. What about water? Water is a little different though. In the situation with water, we have 2 lone pairs, right? So here I've got 2 of the ropes are being pulled. The other 2 ropes don't have a partner to pull them. So there's an asymmetry or an imbalance in the structure to give us a polar molecule. So there's a difference between polar bond and polar molecule. Polar bond is happening between adjacent atoms. Okay, polar molecule is happening within the whole molecule. So it's looking at the whole molecule, not just 2 atoms. So these 2 things don't always parallel. Usually it's a polar bond, right? Because if they're different atoms, they'll be polar. But the molecule is only polar when you have these lone pairs, or when there isn't a vector pulling out to balance it. And sometimes I know that concept throws people off. Dipoles seem to give people trouble all through like Chem 152. So really the simplest thing I can tell you guys is this will cover 98% of it. If you have lone pairs, you're polar. So the lone polar bear should get you through most of it. Non-polar, equal and opposite pull, non-polar, equal and opposite pull. Polar, here, look at what's happening. These are pulling down. There isn't something to pull up. Here we also have polar, right? It isn't balanced and equal. So that's because these, all these things here this has a pair of electrons there that they haven't drawn. This has a pair of electrons here that they haven't drawn. It's creating a polar quality. So let's look at those three that we had done earlier and ask ourselves, is it polar or is it non-polar? Oh, yeah, that is such a mess. So this first one here, would we say that this thing is polar or non-polar? Well, do you see any lone pairs on the central atom? I don't. I see lone pairs on the outer guys, but nothing on the central atom. So no lone pairs, non-polar. Non-polar means it's balanced. Okay, when it looks even and balanced and everything has a partner and everything's distributed nice, that's non-polar. That's like all of our oils and stuff tend to be non-polar. What about this second one here? Polar or non-polar? Well, do we see any lone pairs on the central atom? Yeah, right here. One of our ropes doesn't have a partner, so it's imbalanced. So we're going to go with this thing being polar. So for polar, think of it as being non-balanced. Okay, non-polar is balanced, polar is non-balanced. What about this last one here? Do you see any lone pairs on the central atom? No lone pairs. So we're going to say that this thing is non-polar. It's nice and balanced. And you may be thinking, oh, but doesn't one of them have a double bond? Well, that double bond again kind of oscillates around, so it's balanced enough. All right, so we'd go with non-polar on this. There is one situation in your lab where we get a tetrahedral shape and it is actually polar. I'm going to just draw it out for you. So save this because it will be one of your homeworks. I think it's what is it? CCl-F3. I believe that this is what it is. If it's not this, it's CCl3F. Actually, I think that's what it is. It's like on the very last page, if you have your Vesper lab. Carrie, are you looking at it? You can turn your mute off if you want.
It is CF3Cl.
CF3Cl. Okay, perfect. Thank you. So this one kind of throws people off because they're like, oh my gosh, there's 3 different types of atoms. What's going on here? Well, where is fluorine and chlorine located on the periodic chart? Both of these guys are halogens. So it's real easy to like knock one off and replace it with another one. So those we're going to keep as the outer guys. The carbon will be in the center. So carbon, and then we have 3 fluorines. And then one of them is a chlorine. Okay, so what happened here was there was probably at one time 4 fluorines. One of the fluorines got ripped off and got replaced with a chlorine. How many electrons do I have to play around with here? I have 32 electrons. If you don't believe me, you can add them up, but it is 32 electrons. So what's the first thing I want to do? I want to stick it together. Then I want to make the outer guys happy. So I'm going to add 6 to each of these outer guys. And that will total 32 electrons. And everybody's balanced. Okay. What is the electron geometry here? It is 1, 2, 3, 4, 4, which is tetrahedral. What is the molecular geometry here? Well, do we have any lone pairs on the central atom? No lone pairs on the central atom. So the atoms are doing the same thing that the electrons are doing. They're also making a tetrahedral shape, tetrahedral. But dun, 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 dun. Is it polar or is it non-polar? This is one situation where lone polar bear doesn't work. Do you see how every rope is connected to an atom? But what's going on here? Like this is like, you know, the tug of war. This is the A team here, and this is the B team. Okay, he's not quite as strong as the other ones. So that creates some asymmetry in the molecule, which will actually make this thing polar. Okay. So, you know, you're kind of always wanting to keep your eye out for imbalances. If it's imbalanced, doesn't look symmetrical, it's probably polar. That's one situation where there's no lone pairs on the central atom and it does in fact end up being polar. But really outside of that, lone polar bear is going to get you through 98, 99% of your questions. Any confusion on why that one's polar or what's happening with the polar, nonpolar? Good with why electron and molecular are the same here. All the ropes have a buddy, so the atoms are doing the same thing as the electrons are doing. Okay. So the last thing that I do want to talk about is how this again relates back to oil and water and why they don't mix. So water molecules are polar. If I draw the water molecule OH, H, again, the electrons like to hang out over here. So this side of the molecule has an overall negative charge, where the hydrogens have a positive charge. So what that means is that this water molecule is going to stick to an adjacent water molecule, O, H, H. Okay, here it's negative, here it's positive. And so you get this repeating pattern of one end of one water molecule attaching to one end of another water molecule. That's why water has surface tension to it, or it creates meniscus. It's kind of sticky. So that positive and negative attraction, you can kind of think of it like a magnet, where if I threw a bunch of sand and a bunch of magnets together in, I don't know if they have a drawing of it. I guess they don't. But if I took a bunch of magnets and sand and threw them together in a beaker, what would happen to all the little magnet flecks? All the little magnet flecks would eventually clump together, right? And it would push the sand out. You can kind of think of the water like the magnets. When we put the water with the oil is nonpolar. It doesn't have that positive and negative charge. It's nice and balanced. So all the water molecules clump together and they repel or they push out the oil. So it's not that the oil is clumping together. It's actually that the water is clumping together and the oil is being like left without any other options. So here we can see all the water molecules are clumping together. They're sticking together and they're pushing the oil out. Why does the oil sit on top? That has to do with density. This has a lower density than the water, so it floats. So how does soap work, right? Because you cannot wash your greasy pans with just water. You can't wash your hands if they're greasy with just water. What do you have to use? You have to use a thing called soap. And here's a soap molecule. How do you make soap? Usually you make soap by taking some sort of fat and you run it through a saponification process. So you take, you know, oil, it can be animal fat, it can be vegetable fat, and you use lye and you change the molecule. So normally like fat and oil is nonpolar. So traditionally the molecule would look something very nice and balanced. But when you go through the saponification process, you literally cut off the end of it and you shove a polar molecule on the end of it. So now what used to be, you can kind of originally think of your soap or your oil molecule looking like this, nice and balanced. Well, when you go through the soap process, you shove this thing on there. And now what you have is this long soap molecule where a good majority of it is nonpolar, but there's a little head there that's polar. So likes attract likes. So the polar sticks to the water and the nonpolar sticks to the oil. So the soap molecule is acting as a bridge between these two things that don't want to attract each other, right? The water and the oil don't want to get together, but this long bridge helps bring them together. So now when you wash your hands, the oil attracts to the soap molecule and the water runs the soap off your hands, and then you can have clean hands. And that is it for chapter 10. So now hopefully you know how soap works. You can explain it to your loved ones. So we've got about 15 minutes left, right? Because we go till 10:45. So I'm around. If you guys want to work on some of the problems from the lab, let me know. If you have any questions on this, let me know. If you're done for the day, then I will see you next week. Make sure you get your test done though, or you at least get it started. Yeah, so just let me know. If you want to just kind of hang out and look through your lab, I can just sit here and you can pop in and ask me a question as you see fit. Otherwise, if you're heading out, have a good weekend and I will see you on Monday.
When will you have the lectures for this week on YouTube?
I should have them up tomorrow. I had some issues where I put all my lectures up and none of them downloaded. Something happened with my work computer and they were all set up and none of them got downloaded for 3 weeks. So they should all be up. These ones should be up tomorrow. If you don't see them tomorrow, please email me because my work computer has been giving me a real hard time, okay?
Great, thank you so much.
Yep. Okay, cool. So as long as I see some people on here, I will hang out. Just let me know if you get stuck on a problem.
I think I'm going to head out, but I'm going to work on this. Will you be available for email if there's any questions?
Yeah, I'll be available through email. And if you, Carrie, if you want to send your lab early, like you did with the nomenclature lab, I can take a peek at it before you turn it in at the end, okay?
Okay, because I'm struggling with this one.
Are you? Yeah, get something that you can like sort of three-dimensionally see. And then just play around with doing Lewis dot structures and trying to visualize what it looks like in 3D shape.
Okay.
Normally when we work on the lab, we have these like molecule things that make it, I feel like it makes it a little bit easier. So
probably, yeah. Okay, well,
right, well, yeah, you let me know if you need anything, okay?
Okay, thank you.
All right, bye, Carrie.
Bye.